Similarly, those same equal loudness contour graphs are average, and Dr. McConey said that they are average, the average person. Well, everyone knows that if you look at the average, half of the people in this room are below average and half are above average. And it's the same with hearing acuity. So there's a standard deviation at every point on the equal loudness contour graph. And what we find is that, in fact, 1 person in 7 in this room will sense noise at 6 decibels lower than the average person in this room, and that translates to 4 times as sensitive to noise as the average person in this room. We're all built differently. It's just a fact of life. And yes, it's this person right here. Instinctively, I think, when you hear that, you know something bad's going to happen. And I have that from an expert who never saw or heard of Jaws. He just heard that little clip. Similarly, recent work in medicine, particularly functional MRI, what functional MRI is, it's a map of metabolism in the brain. So there are hard biochemical changes in the brain in response to emotions that we can actually map with functional MRI. And I chose this paper here, which looked at a whole series of emotions: fear, disgust, happiness, etc. Just so happens these 2 emotions, fear and disgust, activated portions of the brain called the limbic system. Have we heard about the limbic system? The limbic system is the basest level of consciousness in our brain. It deals with survival. Fear, hate, sexual arousal, these things activate the limbic system. When the limbic system is activated, there's a release of stress hormones in the body. Similarly, a study from 2002, it's not recent, showed that brain activity is visibly altered following sleep deprivation. These 2 functional MRI images here are summations of 13 people who were asked to do math work without and with being sleep deprived. The top is normal, the bottom are the sleep deprived people. An example of a stress response comes from 1985, where increased diastolic blood pressure in men exposed for 30 minutes to 16 hertz infrasound at 95 dB caused an elevation of blood pressure. Well, we're going to say, well, wind turbines aren't putting anything out over 60 or 70. Well, in fact, you will see evidence today that they are putting out low-frequency noise at very high decibel levels. It just takes the right equipment to look for it. So, can sound be adequately described by decibel level alone? Are both of these paintings blue? Is that all I have to say about them? The one on the right is a masterpiece, and the one on the left is by some guy called Van Gogh. So no, to do so is grossly misleading. But this is routinely done. Dwelling, vibration, and rattle. And this is just one of the few graphs I'm going to show you, because this is critical. And this is not rocket science. This is fairly old science. What we have on the left is a tracing. It's a tracing of it's a frequency spectrum from a series of wind turbines being recorded on the facade of a house 2,100 feet from a large wind turbine collection done on the German-Dutch border. And this is done by G.P. Vandenberg, the same Vandenberg that Dr. McConey referred to. And what does he say? He said infrasound levels from large turbines may cause structural elements of buildings to vibrate. The vibrations may produce higher frequency audible sound. So yes, technically it's true. Most of us will not hear low frequency sound. But our buildings will change it into something. They're doing us the favor of changing low frequency sound into something that we can hear. What you have on the left is one of the newer technology sound recording methodologies. The temporal and frequency resolution of this is many times more what your typical acoustician who does contract work for wind industry companies have. This is the equivalent of acoustician rocket science. And what you see here, and it's a little bit difficult to understand, but the colors reflect the volume, and the height that the colors reach are the frequencies that they affect. And the important thing here is to know that we have 90 decibel and above measured at 20 hertz and below. This is outdoors, 1,500 feet from a 1.5 megawatt turbine in Michigan. Now, why haven't we known this up till now? And the answer is simple. The sound recording equipment and the sound analyzing equipment has a window during which it collects that sound. If that window is too wide, the peaks get averaged out, and you don't see those high-frequency peaks. What you have on the right is this is a very standard graph from a building science textbook that shows for typical consumer residential housing at what frequency and at what decibel you will have rattling of different components of the home. So we have windows, walls, and floors. The red dots are points plotted based on the information on the left graph. So everything to the left of this line of red dots is occurring, and we can expect windows, walls, and floors to rattle, at least in the vicinity of this wind turbine. This is a home that was bought by a wind developer in Amaranth, Melanchthon, up in Ontario. And the tent you see out there was the structure that the residents slept in until the home was bought. And what you have below is a quote from her journal. "The house is humming again tonight, incredibly horrible. I don't know how much of this we can take. Reach my limit, there is no escape." Well, it's a qualitative statement, but it does make sense in terms of what we know about buildings and how they respond to low-frequency noise. You don't have to hear it yourself. Now, one of the authors of the AWEA report said, "I can state quite categorically that there's no significant infrasound from current designs of wind turbines. Infrasound is not a problem. The regular swish is not low-frequency noise." Now, a year before, he had said, "Regulatory authorities must accept that annoyance by low-frequency noise presents a real problem which is not addressed by the commonly used assessment methods." Which statement is more correct? The 2004 statement is correct, and he knows it. 2005 is kind of a different tune. So this is a more extended version from that same 1.5 megawatt GE turbine. We have peaks of 90 dB and greater at 20 hertz. Here's the pulsatile blade swish, and everyone acknowledges that we hear the blade swish. Now, is that okay? So if we go back to the AWEA author's statement, he can state quite categorically that there's no significant infrasound from turbines. No. Infrasound is not a problem. No. The regular swish is not low-frequency noise. Technically correct. It's like saying when you fall off a building, it's not the falling that kills you. It's when you hit the sidewalk. This is where blade swish is. Blade swish is sort of right in the middle of the equal loudness contour graph. And we've heard from Dr. McCunney that if you are 20 dB above the threshold, people start to find that objectionable. Well, here we are. We're 30. I'm going to talk about Mars Hill. We have 28 turbines there. They went online in December '06. There's about 30 adults and 15 children who live within 3,500 feet. This is where Mars Hill is, up here in the north. Far away from all the wind is, you'll note.